Okay, our example 4 of optimization problems, we can read a closed box, that means one with a top and a bottom, with a square base, so this box has a square base, is to have a volume of 16,000 square inches, pretty big box. The material for the top and bottom of the box costs 30 cents per square inch, and the material for the sides costs 15 cents per square inch. Find the dimensions of the box that will lead to the minimum total cost, and what is that minimum total cost? As you see, I've already I've already started my diagram, and I'm going to label the dimensions of the base, the length and the width. Remember, this is a square base, and so both of those dimensions are x. And I think I'll label the height, I could label it h, but I'm going to label it y. Now again, we need to pay attention to what's being asked of us, and we're asked for the minimum total cost. And so we have to determine a cost function. Say our primary function, or excuse me, our primary equation is about cost. So we need to decide how we're going to determine the cost. And you see that we have the sides cost one amount, the material for the sides cost one amount, and the material for the top and bottom cost another amount. And so let's just kind of think through this. That is, we're discussing the cost of maybe the top. Well, it's going to be 30 cents per square foot, that's $0.3, 30 cents per square inch, times the area, okay, of that. So the area is going to be in square inches, and we need to know that it's 30 cents per each one of those square inches. So the cost of the top will be 0.30, and of course the area is x times x, because each dimension is x. And so that ends up being 0.3 times x squared. In a similar fashion, the cost of the bottom is also 30 cents per square inch times the area of the bottom, which is x times x, or x squared, and so we get 0.3 x squared again. Now the cost for a side. Now the side, the material just costs 15 cents, or $0.15, times the area of a side. But the area of a side has one dimension x, and the other dimension is y. So we get 0.15 times xy. But there are 4 sides, okay? So don't forget that there are 4 sides. So our cost equation, cost would be equal to the cost of the top plus the cost of the bottom plus the cost of 4 sides, and so we'll say 4 times the cost of a side. And so as we put these pieces together, the top being costing 0.3x squared, and the bottom cost being 0.3x squared, and 4 times the cost of a side, and cost of a side is 0.15xy. And as we simplify that, 0.3 times 0.3 is 0.6x squared, and 4 times 0.15 is 0.6xy. So there's our primary equation is a cost equation, and there is our primary equation. But we see that we've got an extra variable y, and so we need to come up with a secondary equation so that we can eliminate y. Well, the piece of information we have for the secondary equation is that we know that the volume has to be in 16,000 square inches. So something about volume, well, volume is length times width times height, isn't it? And in this case, the length is x, the width is x, and the height is y. And we know specifically that our volume has to be 16,000. And so we have to have 16,000 equal x squared times y. And we ought to be able to solve this for y, easily done. Y would be 16,000 divided by x squared. So we can use this information then back up here with the original cost equation. So we can eliminate the y value by replacing it with 16,000 over x squared. So we have 0.6x squared plus 0.6x times, instead of y, the fraction 16,000 over x squared. And as we simplify a little further, that's going to be 0.6x squared plus x over x squared is going to leave an x in the denominator, and 0.6 times 16 is 9,600. So that's what our equation looks like. Now, we need the critical number. See, we're trying to minimize the cost, and so we need to find out where these critical values are. Well, to do that, we need to find the derivative, don't we? And I tell you what, before I find the derivative, let me write this as 0.6x squared plus 9,600 times x to the negative 1. That will help me calculate the derivative more readily. 2 times 0.6 is 1.2, so we have 1.2x. And then we have minus 9,600 times x to the negative 2 power. And I can write that as a 1.2x minus 9,600 divided by x squared. That might be useful here in a moment. So notice that we have critical numbers, c prime being equal to 0. We need to solve the equation 1.2x minus 9,600 over x squared is equal to 0. And then for c prime being undefined, well, we can look real easily and see that it's undefined when x is 0, isn't it? That derivative is undefined because we have x in the denominator, x squared in the denominator. So we have one critical number of 0. Now it's going to take us a little more work to solve this equation. Let's do that on the next page. Okay, well, to solve this equation, I'm first going to get rid of the denominator x squared. And so I'm going to multiply all the way through by an x squared, and that will become 1.2x cubed in this position. And of course, the x squared will cancel from this fraction, and x squared times 0 is still 0. And then I don't like this decimal, so I'm going to multiply all the way through by 10, and I'll get 12x cubed minus 96,000 when I multiply by 10 is equal to, and 10 times 0 is still 0. So I need to solve for x here, and the easiest thing to do would be to isolate the x cubed. And so I'll add 96,000 to both sides, and then I'll divide on both sides by 12. Okay, I'll come up here to save a little space. Let's see, 12 goes into 96 how many times? 8 times. And so I actually get x cubed is equal to 8,000. And so that means x itself. Now here we don't have plus or minus because we're talking about a cube root. And a cube root is not going to give us a positive and negative. It's just going to give either a positive or a negative. And in this case, it wouldn't take us very long to figure out that the x would be, 20? I believe. 20 times 20 is 400, times another 20 is 400. 20 times 20 is 400, pardon me, and then multiply by 20 again, and we get 8,000. Or we could maybe use our calculator, but we get x equal 20. So, in summary here, our critical numbers are x equals 0 and x equal 20. Now, in this case, we have an additional problem that we haven't run into before. Let me write down our cost function. say, and I'm pairing back on the previous page, and our cost function is 0.6x squared plus 9600 divided by x. Well, there's and what is x? X is a dimension, isn't it? See, x is the measurement of the side of the base. It's the base side measurement. And we have an immediate problem here. Before we've been able to say, okay, well, since this is a measurement, x could be as small as 0. But in this case, we're talking about cost function. And in the cost function, if we let x be 0, we get an undefined cost, don't we? So x can't be 0, and so we can't have a closed interval. See, we can't say our interval starts at 0 and includes 0. This is not going to be allowed, and so we can't create a closed interval. Now, what we could do instead is we could determine whether this 20 value, I mean, obviously 0 is not going to be allowed, and on the left side of 0 we have costs that would be that would not make sense because x's would be negative. That doesn't make sense. So we might as well assume that x is greater than 0. So when we assume that situation, okay, let's think about what's going on here. What I want to know is, does the critical number 20 give me a maximum or a minimum? And let me kind of imagine the first derivative test situation. In fact, we could actually use x equals 0. Okay, that's a critical number where the function's undefined. And then we could consider x equal 20. Now this is going to be enlightening, I believe. Okay, so here we would be talking about, and we're talking about this function, and although it doesn't make any sense for x's to be less than 0 or equal to 0, the function would be defined from negative infinity up to 0, wouldn't it? And the function is certainly defined between 0 and 20, and the function is defined between 20 and infinity. Now, what I think would be reasonable for us to do is to test the first derivative. And now let me also let's write that first derivative down. Isn't the first derivative equal to 1.2x minus 9600 divided by x squared? And so what I would tell you that if we choose an x value that is in this interval, those are negative x values. And so I'd have 1.2 times a negative value over here. See, I'd have 1.2 times a negative value. And when I square that negative value, I get a positive. So I'm subtracting a positive fraction. Negative subtract positive is going to give a negative value. And so that tells me that the cost is increasing. Increasing. Now we can't have a x value of 0, so we have to skip over that, but we need to test a value between 0 and 20. And so when we test a value, now what are we testing? The derivative here. We get c prime of 10. I'm going to choose 10, and that would be 1.2 times 10, which is 12, wouldn't it? Minus 9600 divided by 10 squared, which is 100. And so that would end up being what? 12 minus 9.6, which most importantly is positive. So now we have the cost function increasing. Hold on just a moment. Well, I apologize here. I've made a couple of errors. Okay, talking and writing gives me some trouble once in a while, I see. Okay, here's the situation. that between negative infinity and 0, our derivative is negative. And so that means, of course, the function is decreasing. But we really don't even care about that, do we? Because we can't have x's that are negative. But it's kind of important to know the big picture. Now, I made a calculation error over here, is that when I chose x to be 10, and I'm testing the derivative when x is 10, and 1.2 times 10 is 12, but 9600 divided by 10 squared is 9600 divided by 100. And 9600 divided by 100 is 96. And 12 minus 96 is negative. So this function is decreasing. Okay? And then when I choose a value that is bigger than 20, like maybe 100, okay, well then that would be 1.2 times 100 would be what, 120? And then I'd have 9600 divided by 100 squared, which will be 10,000. Okay, well clearly that's a number that's smaller than 1, and 120 minus something smaller than 1 is certainly going to be positive, isn't it? So here the derivative is positive, so that means the function is increasing. Now here's the point. We're decreasing, we're not considering 0, x equals 0 or less than 0. So when we're bigger than 0, we're decreasing, and then we start increasing when x is 20, and we're increasing ever after, okay? So this relative minimum is actually what we're looking for. In this case, it happens to be also an absolute minimum from 0 to infinity, not less than 0, but from 0 to infinity. And so we're very interested in this value, and that's when x is 20, isn't it? Okay, so what we found out is the minimum cost, minimum cost occurs when x is 20. Now, what's our original problem? Our problem is to find what the minimum cost is, and we also need to know the dimensions that create that minimum cost. So let's talk about first the dimensions. Well, remember the dimensions are x by y. And of course, we're measuring in inches, aren't we? So x is actually equal to 20 inches. So that's a 20-inch, the base is 20 inches by 20 inches by, now y, what was y? We had a formula for y when we solved for y. And our y formula ended up being 16,000 divided by x squared. So our y value is 16,000 divided by x squared. In the case that x has to be 20, that's 16,000 divided by 20 squared. Well, that's 16,000 divided by 400, which is equal to 40. Okay, so y is 40 inches. So the dimensions 20 by 20 by 40, the base 20 by 20, and the height 40 inches, well, that's a pretty darn big box, isn't it? Gives the minimum cost. This is when we have the minimum cost. Now, what is the minimum cost? Okay, well, what is the cost function? The cost function is 0.6x squared plus 9600 divided by x. So in this case, our x has to be 20 to get the minimum cost, so that's 0.6 times 20 squared plus 9600 divided by 20. Well, let's see. 20 squared is 400, so this is 0.6 times 400. And 9600 divided by 20 is what? Oh, what is that, 480? I believe that's 480. Okay, double check me there, but I believe that's correct. So 0.6 times 400 is 240 plus 480. Of course, it's a big box, okay? So the cost is, what is that, $720, isn't it? The cost of this box is $720. That's the minimum cost, and that's if we use these dimensions up here. So being such a big box and the material is fairly expensive per square inch, then the minimum cost for this box is $720. Okay, we have one last problem, and we'll begin it momentarily. Okay, example 5 of our optimization problems is stated here that we had a liquid form of an antibiotic manufactured by a pharmaceutical firm is sold in bulk at a price of $200 per unit. If the total cost in dollars is for X units is given by the function or the formula, cost of X units is equal to 500,000 plus 80X plus 0.003X squared. And if the production capacity of the firm is at most 30,000 units in a month, how many units of antibiotic must be manufactured and sold in a month to maximize profit? A lot of words, isn't it? Well, I can't create a diagram for this. This is not geometric at all, is it? But what I can do is focus on maximize profit. So the very first thing I'm thinking is that my primary equation must have to do with profit. Whoops, equation. Okay, has to be profit. That's what I'm maximizing. Now, I don't have anything that tells me about profit, but this is something that probably we should already understand. That profit is the amount of money we make when we subtract the cost from how much revenue. So profit basically is total revenue. So that would be the amount of sales that how much money we make from sales, subtract the cost to produce the units that we sold. So profit is nothing but revenue minus cost. Now, revenue is something else that we need. So here's kind of where we are. Our profit function, our profit equation, P I'll call it, is going to be revenue minus cost. But cost we have above. The cost for X units is 500,000 plus 80X plus 0.003X squared. So we need to decide what this revenue is before we can actually calculate our profit equation. Okay? Well, revenue is the amount of money we make by selling the product. So the revenue in this case, how much does the product sell for? $200 per unit. And if we sell X units, then the revenue will be 200 times each of those units, 200X. So now we're set up to complete our profit equation or our profit function. It's our revenue 200X minus 500,000. Remember, this all is the cost in here, and it needs to be in parentheses because we're subtracting the whole thing, aren't we? So that simplifies to 200X minus 500,000, and that's an 80X there. Sorry about that. 500,000 minus an 80X and minus a 0.003X squared. And I see I have 200X and I have minus 80X, so that simplifies further as, let's write this as Now, let's do this. We'll say negative 500,000. 200x minus 80x is positive 120x, isn't it? And then minus 0.003x squared. So I need critical numbers, okay? And so I need to find P prime. And of course, the derivative of a negative 500,000 is just 0. The derivative of 120x is 120. And then it'll be what? Minus 0.006, 2 times 0.003, and reduce the exponent by 1, so times x. Now, where does that leave us? Oh, we need to find out where this is 0, don't we? So we'll set it to 0, and we'll solve. Okay, so I would add 0.006x to both sides, so I'd have 120 is equal to positive 0.006x. Divide both sides by the decimal, 0.006, and that's my x value. And when we calculate that, what do we get? Let's say we get an x value of 20,000. Now, let's see if we can squeeze things in here a bit, kind of getting this a little bit messy. What about our feasible domain? Our last problem, we didn't have a closed interval to consider, but in this case, we easily can come up with a closed interval because we certainly can produce 0 units. Our profit would just be negative 500,000, which represents the operating cost. The fixed cost. I mean, anytime you're in some kind of business, there are costs that you pay, whether you're open for business, whether you're manufacturing or not. You've got rent, you've got insurance. There are things that you pay for that are not related to the manufacturing or even the retail business if you're in a retail business. So we could certainly produce 0. We would just go in the hole, wouldn't we? Now, it also tells us, though, that the capacity, the manufacturing capacity is 30,000 units in a month. So we can't produce more than 30,000, and we can't produce less than 0, but our feasible domain is between 0 and 30,000, closed interval. And certainly this critical number falls in that category, doesn't it? So we're now in a situation where we really have 2 endpoints to consider. So they are x values to consider, whether it be an x value of 0. And actually, I know that I need to make more space here. So let me do this. We could have an x value of 0, and we want to know we're looking for the maximum profit. Okay, so we could have an x value of 0. We're going to test the critical number 20,000, and then of course we could go to a capacity of 30,000. And remember, for an absolute maximum on a closed interval of a continuous function, then that absolute maximum and, of course, the absolute minimum are going to occur either at the endpoints or at the critical numbers, and that's what we've listed here. Well, when we put 0 in for x in the profit function, and remember, this is the profit function that we're talking about, we put 0 in for x and we get negative 500,000. Oh, that's not good, is it? Well, okay, what happens when we put 20,000 in? And we just need to do the calculations. Well, we need to put 20,000 into the profit function, okay? So we'd have negative 500,000 plus 120 times 20,000 minus 0.003 times 20,000 squared. When we do, we'll get a value of 700,000. And then we also need to check when we put 30,000 in, okay, And when we put 30,000 in for X, that's the number of units, into the profit function, we would actually calculate and get 400,000. Now, I remember a long time ago, I warned you that don't always expect at the endpoints that we're going to get 0. See, here we have an absolute minimum of negative 500,000. Of course, that's not what we're looking for. We're looking for a maximum. And so we need to produce 20,000 units for a maximum profit a maximum profit of $700,000. Okay. And so the answer, of course, is that we needed to produce 20,000 units. Now, this seems counterintuitive at first, because most of us think that if we can produce 30, the more we produce and the more we sell, then the more we ought to have in profit. But what many people overlook when you're in business, to run at capacity, see, to run, the difference between making 20,000 units in a month and 30,000 units in a month may require, for instance, that we add an extra shift. And if we add extra shift, we have greater labor costs that we didn't have before. And we have maybe greater electrical costs. And, there are other things. Of course, we certainly have more material costs, don't we? But it's all of those additional costs that may actually make our profit go down. And that's actually what we see here. The optimum amount to make is 20,000 based on the information we have. That will give us the maximum profit. Well, here ends our examples for optimization. I hope that you find them useful. Good luck on your homework and, of course, studying for a test.